Good day, everyone. So, we are here to discuss our research topic that is about the design and evaluation of piezoelectric sensor based train approach detection and alarm system. So, to start the presentation, we have Miss Aquino.
For our introduction, as the researchers saw that the Philippines railway system is facing some safety issues. Piezoelectric sensors offer a solution by detecting train vibration to trigger alarms, featuring adjustable sensitivity and low maintenance. For our background of the study, the Philippines railway system struggles with human errors, outdated technology, and poor maintenance. Piezoelectric sensors offer a improved and real-time detection but required further research on integration, reliability, and cost-effectiveness. For our objective of the study, as the researchers is assessing the use of piezoelectric sensor to enhance train detection, automation, and safety, addressing rural areas technologies deficiency. For our next presenter will be Mr. Cellona.
Let's talk about scope and limitations. Sa scope ng aming project, it detects train vibration to trigger visual and audible alarms like on a system, madidetect niya yung vibration, it would alarm the authorities that na may parating na tren. Also, the hardware design includes piezoelectric sensors, amplifiers, and alarm mechanisms. And also potential additional features such as real-time data transmission and monitoring connected to a system or a server to have a real-time management of the data. The limitations is that it's sensitive to environmental factors such as temperature, humidity, since at the end of the day, it is still a electronic device and can be vulnerable to environmental changes and environmental factors. It also needs periodic maintenance since kalaban ng mga electronics ay oxidation, water and humidity so para maprotektahan at for the long term ang circuits. Significance of the study. Ang aming significant to sa mga drivers, pedestrians at railway authorities dahil nadedetect no ng sensors yung mga oncoming trains para matulungan sila. Thank you.
And these are foreign-related literature that offers a broader perspective but for our study, which focused on railway safety systems. This could include international case studies of similar systems using piezoelectric sensors. And first we have transducers converting electromagnetic wave into sound wave. Second, a sensor for rail project from McLaughlin in 2021. Agency train detection system for employing ultrasonic and microwave sensors. Use of piezoelectric sensors to effectively detecting structural vibrations. Piezoelectric transduction, so for ultra low frequency, piezoelectric energy harvester. And lastly, piezoelectric energy transducer used in railborne energy harvesting. So these are local related literatures that provides insights into existing systems, practices, and knowledge about our study, starting from piezoelectric shoes in pedestrian crossing, piezoelectric transducers for LED street lights that generates power, train-generated electricity system for producing energy from rain and sunlight, vibration-based energy conversion for wireless sensors. Lastly, efficiently converting of environmental mechanical force into power.
I will now discuss foreign related studies. Piezoelectric sensors are widely used for detecting dynamic forces in structural health monitoring and vibration control, excelling in frequency analysis over optical fiber sensors. Their integration with Arduino microcontrollers facilitates real-time data processing and IoT applications, especially with renewable energy sources like solar panels powering these systems. Now, for local related studies. In the Philippines, technologies like Intelligent Transport Systems or ITS improve traffic management while piezoelectric materials are explored for renewable energy applications, such as energy harvesting from roads and stairs. Advanced sensors are also utilized for precise environmental monitoring, emphasizing sustainability, and efficiency. Now, for synthesis. Piezoelectric sensors combined with Arduino microcontrollers and solar-powered systems offer a cost-effective solution for real-time terrain detection and monitoring. These systems align with sustainability goals and Industry 4.0, making them ideal for smart infrastructure and renewable energy initiatives in remote railway networks. The next part will be discussed by Ms. Pimentel.
My name is Kathrina and I'm discussing the conceptual framework of our study. So first thing, we have the 4 steps or 4 parts of the procedure, starting from the input, which is for sensors and detection. The data is captured using piezoelectric sensors, then converted and processed into usable signals. Second part is for the signal processing and decision making. Signals are filtered, analyzed using detection algorithms, and evaluated to trigger alarms based on set thresholds. Third part is for the output or design for alarm systems. Decision outputs activate alarms, visual or audio alerts, and safety action to address identified risk. Last part is for the evaluation and feedback. System performance is tested using metrics like accuracy and response time, with findings for continuous adjustment to improve reliability and operation. So that's the end of the chapter 2. Moving forward, we have our research methodology from chapter 3, starting from the research design, which employs descriptive research to innovate the piezoelectric system by analyzing data to identify areas for improvement. The process involves either interactive design approach, where requirements are analyzed, a quick design is created and refined, and a detailed design is finalized as well, or the prototype-driven approach, where a prototype is built, tested, refined, and transitioned into detailed design, implementation, and maintenance. Both method ensures adaptability and practice testing for effective system development. Then we also have our gathering requirements and analysis. So our railway safety system for Metro Manila was conceptualized using piezoelectric sensors, microcontrollers, alarms, and power systems. A comparative study of similar system was conducted to identify best practices, ensuring an effective and contextually relevant design.
Thank you, Ms. Pimentel. 3.3 Quick Design. Created a 3D model using AutoCAD incorporating all required components. A simulated system operation in a virtual environment to identify potential issues. 3.4 Constructing the prototype. Prototype components consisting piezoelectric sensor, microcontroller, voltage regulator, battery, solar panel, and buzzer. The purpose of the sensor signals is to activate the buzzer through the microcontroller, while the solar panel ensured a sustainable power source. 3.5 Evaluation of the prototype. The pros in this prototype is simple design, low cost, and easy to construct, but the downside or cons is limited functionality. Did not utilize microcontroller's full potential. 3.6 Detailed design. Enhance the system design to address initial limitations. Focus on both hardware and software improvements. Adjusted features for better reliability and performance. So here is Ms. Villanueva to report the next part.
The project involved the iterative design, testing, and refinement of a railway detection system, addressing key challenges in system architecture, sensor placement, and alert algorithms. These refinements continued until the system fully met the necessary requirements. A physical prototype was deployed at the Philippine National Railways, or PNR, where it underwent extensive testing, including programming, data collection, signal processing, and alarm activation. The system was initially calibrated without the presence of a train, and then tested with a variable speed locomotive on a designated railway track. Regular maintenance and performance assessments were conducted to ensure reliability, with PNR overseeing operations and supporting the ongoing process. The system sensor detected train vibrations, triggering alarms when trains approached. Additionally, the system underwent field testing under varying weather conditions to assess performance, evaluate alarm response, and monitor power efficiency. Feedback from these tests led to continuous improvements with regular recalibration and updates made to ensure optimal functionality in real-world conditions.
And to end our presentation, these are the references for our research. That is all. Thank you for listening to us.